Everyone, we're getting close to the end for trigonometry here at College of the Sequoias. In the last section, what we looked at was, last section was complex numbers and turning them into their polar form or their trig form. Okay, that was 8.5. We're going to expand on that a little bit in this section. 8.6 is on powers and roots of complex numbers. And something called de Moivre's theorem. Sorry, that's a capital M. De Moivre's, and it's spelled funny. I think he's French, looks French. And it goes something like this. So recall we had something like A plus BI, and we could write that as R cosine theta plus R sine theta I. Okay, that's what we did before. What happens if we add an exponent to this? What if I have something like I square this? Like it says, powers of complex numbers. Let's square this side. And what happens here? So this is really R cis theta squared. Let's write it out. Remember, when we square it, we have two parentheses multiplied together. And we have to distribute. So the first one, we've got R squared cosine squared theta. And then I send it outside. I get R squared cosine theta sine theta I. And then inside, I have another one of those, R squared cosine theta sine theta I. And finally, I end up with R squared sine squared theta I squared. This I squared over here, though, this turns into -1, right? So this is a real term. This is a real term. This is a complex term, and this is a complex term. Let's group them. So I've got R cis theta squared. I've got, it looks like I'm taking R squared out of everything, right? And then I got cosine squared theta minus sine squared theta. And then for my I, I've got R squared again. And it looks like I've got 2 cosine theta sine theta, which looks a little funny in the form I wrote it, but it should look familiar. Do we have any formulas for anything that's present? We do. This is 2 cosine theta, or cosine 2 theta, sorry. And this one is sine 2 theta. So this was my R cis theta squared. And I can write this in a similar form. I've got R cis theta squared equals R squared cis of 2 theta. Do you guys see that? They both have the same angle inside, it's 2 theta. So we can put it together like this. Well, it may not be clear yet. Let's do one more. Let's do one more. Let's look at r cis theta cubed. Well, that equals r cis theta squared times r cis theta. And we just wrote out what r cis theta squared was. So I've got r squared times cosine of 2 theta plus I sine of 2 theta. That's this first one. And then I've got r cosine of theta plus I sine theta. And that's this one. Let's distribute again. Let's see what happens. So the r squared times r is r cubed. And if I distribute this, I get cosine 2 theta cosine theta. That's the outside. And then I get cosine 2 theta sine theta I. And sine 2 theta cosine theta I. And finally, sine of 2 theta sine of theta I squared. And this is going to turn to -1. So again, these are the real terms. And we'll group them together. So r cis theta cubed is r cubed. Then I've got cosine 2 theta cosine theta plus sine 2 theta sine theta. Nope, minus sine theta. Sine 2 theta is sine theta because the I squared goes to negative. And then plus so I've got, let's put them in the same order. Cosine 2 theta sine theta plus cosine theta sine 2 theta. And that's in our I direction. This should look familiar. This is cosine of A plus B. And this should look familiar. That's sine of A plus B. So if we put them together, A is 2 theta, B is theta. So 2 theta plus theta is 3 theta. I've got cosine 3 theta plus, and then I get down to this parentheses, this turns into sine of 2 theta plus theta is sine of 3 theta, but we have the I there. And finally, r cis theta cubed is r cubed cis 3 theta. Now, I could keep doing this. I could keep going on and on and on and finding a next power and the next power and the next power. But have you guys noticed a trend? When I had r cis theta squared, I got a square on my r and my angle went double. When I did it cubed, my r gets cubed and my angle goes triple. In fact, this is de Moivre's theorem. r cis theta to the nth power is equal to r to the nth power cis n theta. We just showed it for n equals 2, n equals 3. And by default, it's what it means when n equals 1. And you could keep going with this. Okay. Let's use that. Let's use that to our advantage. Let's like try to solve a problem real quick. Okay. I hope this is important. Box it, learn it. It shows up a lot throughout here on out. And it might be a little while into calculus before you see it again. But once you start working with exponentials and how they break down into sine and cosine functions, they're there all the time. So here's an example. Let's find square root of 2 plus I root 2 to the 5th power. Okay, well, what can we do here? Well, right now, this is in a plus bi to the 5th power form. And I want it to be in r cis theta to the 5th power form to use that formula. So this takes us back to 8.5. What do? This is like my x. This is like my y. And we had x equals r cosine theta, y equals r sine theta. Which is root 2 and root 2. Where does that happen? Well, since it's root 2, what does that look like to you? It's a lot like root 2 over 2, isn't it? Right? This looks like if I cut this in half, if that was root 2 over 2, we'd be good. Because that would be 45 degrees. Right? So how did we find it before? What did we do? Let's look back at our notes. R equals the square root of x squared plus y squared. And we did tangent theta equals y over x. We'll do that here. Does my intuition translate? This looks like maybe it's going to be 45 degrees, but the radius is off. Maybe I need to double the radius or something. Let's take a look. R is the square root of the square root of 2 squared plus the square root of 2 squared. So R is the square root of 2 plus 2, which is the square root of 4, which is 2. And tangent theta, y over x, root 2 over root 2 is 1. And we know that's when theta is 45 degrees, or pi over 4 in radians. So let's rewrite what we had. Let's rewrite this in r cis theta form. I've got 2 cis 45 to the 5th power. The rules were we apply the exponent to the 2, and we treat that 5 as a multiplier times the 45 degrees. 2 to the 5th power is 32. This is cis of 225. And where is that? That's 180 degrees. That's right here. We've got a reference angle of 45 degrees. And in quadrant 3, sine and cosine are negative. So this turns into, I've got 32 times cosine of 225 plus 32i sine of 225. And both of these are negative root 2 over 2. And 32, I divide by 2, I get 16. I get negative 16 root 2 plus negative 16 I root 2. And I guess I don't need the plus and the minus. We can just do the minus. Okay. So let's go a little bit further with this. I started this off with saying we had a plus bi squared, and that was r cis theta squared. I'm going to look at that again. We eventually moved on to this 2 being an n. So let's do that here. We've got r cis theta to the nth power. And that's really a plus bi, some real component, some imaginary component to the nth power. And there's a rule for complex number. This is called the nth root rule. For a positive integer n, the complex number a plus bi has an nth root of the complex number x plus yi. So a plus bi is an nth root, not has, is an nth root of x plus yi if a plus bi to the nth power equals x plus yi. Now, that's a little tricky on the wording, right? I agree. Let's bring up another example that we can take a look at. Let's see, they got a good one in the lecture notes or in the actual book. Let's take a look at it. And then we'll do some of our own. Example, find the 3 complex roots of 8 cis 135. Okay. So this is 8 cosine of 135 plus I sine of 135 And I got the 8 out in front in parentheses. And it says there's 3 roots. So this means this is r cosine theta plus I sine theta cubed. And we just showed that means this is r cubed cosine 3 theta plus I sine of 3 theta. That was de Moivre's theorem. And so what we do is we start matching up stuff. 8 matches up with r cubed. So r cubed equals 8. And if I take the cube root of both sides, I get r equals 2. The only difference in the parentheses are the angles and what they match up with over here. It looks like 3 theta has to equal 135 degrees. But also every time we go around the circle 360 degrees, it also equals that. And we'll say it can go around k times. It can go around a lot. So we find theta. And we get theta equals 45 degrees plus 120 degrees times k. So what does that tell us our 3 roots are? Our solutions are we get r equals 2, 2 cosine or 2 cis 45 degrees. This is when k equals 1. Then we have 2 cis. We'll add 120 to it. This is 165 degrees now. That's when k equals 2. I'm sorry, this is k equals 0. That's k equals 1. And finally, we add another 120 degrees. We get 285 degrees. And that's when k equals 2. Those are the 3 roots. They have another way of writing this theorem. I'll show it to you. I don't know how helpful it is. We're going to do some more examples. But I thought you should see them. So it's called the Nth Root Theorem. So again, n is a positive integer. R is a positive real number. It can be irrational, but not complex. We'll have theta in degrees. If those things happen, then, if those are all the situations, then the non-zero complex number r cis theta has exactly n has exactly n distinct roots. And they're of the following form. The roots are, we will have the nth root of r, and then cosine, they use alpha. I think alpha looks funky. I'm going to use beta plus I sine beta. And the important thing is where beta equals theta plus 360 degrees K divided by n, just like we did in the last problem. And that's separatable. You can do it like this. And K goes from 0 up to n minus 1. The reason why it stops at n minus 1, the nth term starts to repeat. In fact, it repeats the k equals 0 term. You can do this in radians. If you do this in radians, the only difference in theta and radians, it just changes the way beta looks. Beta is theta plus 2 pi k over n, or theta over n plus 2 pi over nk. Okay, we did do this, and what we just did, I went with a little bit more of an approach where it felt like let's line stuff up. I think it's a little bit more intuitive to look at lining it up rather than going, here's this magic formula, look at this, how it works. So let's do some more of that. Let's take a look at another example. Pause this if you need this written down a little bit more. Okay. So let's find the 3 cube roots of negative 27. Okay. So what we need to try to do is write negative 27 in complex form and then in trig form kind of thing. Well, in the complex plane, we've got x and yi. Negative 27 is due left. This looks like it's making an angle of 180 degrees. And how long's the radius? R equals 27. So I've got, we're going to rewrite it. We've got negative 27, which equals negative 27 cosine of 180. I'm sorry, positive 27 cosine of 180 plus I sine of 180. And that has to match up with r cubed cis theta, or cis 3 theta, because it's the 3 cube roots. If you want to use the formulas we just had, let me put it back up. So what do my letters line up with here? N equals 3, R equals 27, I'm not sure what beta equals. Oh, wait. No, it changes. It's a multiple thing. I do know theta here is 180 degrees. There we go. So what does beta equal? Is 180 degrees plus 360 degrees times k over n, which was 3. Beta equals 60 degrees plus 120 degrees k. And we know k goes from 0, 1 to 2. It stops at 3 because then it would repeat. So the possible angles we have are 60 degrees, 180 degrees, 300 degrees. R is not 27, R cubed is 27, right? So R is 3. Yeah, R was 27. The form I had it written to match up with the formula I have, R is 27 and it matches up with that. So I've got these angles, my 3 cube roots, the 3 cube roots of negative 27 are 3 cis 60, 3 cis 180, and 3 cis 300. Let me let you guys try this on one and see what you come up with. So our example, I'll hit pause for a while, or I'll delay. You should hit pause too. Find the 4 roots of negative 128 minus 128 I root 3. And we want them in rectangular form. So this last time I stopped in trig form. In this example, we'll finish it out. Okay, so what do we have here? We got to figure out what angles we've got going on. We know we've got n equals 4 because there's 4 roots, right? Here, x is negative 128. Y is negative 128 root 3. This is in the 3rd quadrant. So tangent theta equals y over x, negative 128 root 3 over negative 128, which gets me root 3. What's my reference angle? Where does tangent equal root 3? Hopefully you came up with theta hat is 60 degrees, which means we're going to add 60 to 180 And this tells us theta equals 240 degrees. What about r? And this is the square root. I'm going to be smart about this. I've got 128 squared times 1 squared plus root 3 squared. Hopefully you like this little bit of clever math. 128 squared and 4 squared, which means I can make the square root apply to each of these. I've got 128 times 4, and what is that? 512? I caught. So what do I have here? I've got 512 cis 240. Now we're going to try to take the fourth root of this, which looks like that's going to be fun. Let's take the square root of it twice. The fourth root of 512 is the square root of the square root of 512. Let's see if there's another way of writing this. Let's see, 128 is 64. Is 64 times 2. This is 8 times 8. This is 2 cubed, 2 cubed. I got a 2. Then I'm times 4, and that means I got another 2 and another 2. So I've got a total of 3, 6, 9 2s. I'm looking for the fourth root of 2 to the 9th power. Which means I should be able to pull out a 2 squared and still have the fourth root of 2 on the inside. Are they the same thing? I guess I do have a button right here that has it. So I'm going to do 4. Approximately 4.76. What happens if I do 4 times, 4 shift root 2? Yeah, so these are the same. I'm going to go with this one, or 4 to the 4th times the fourth root of 2. So that'll be my R. I've got 240 degrees. The cis 240 needs to match up with cis of 4 theta. So 4 theta equals 240 degrees plus 360 degrees K. Theta equals 60 degrees plus 90 degrees times K. And my 4 roots, 4 times the fourth root of 2, cis 60. 4 times the fourth root of 2, cis 150. 4 times the fourth root of 2, cis, we add another 90 is 240. And finally, 4 times the 4th root of 2, cis of 330. They wanted our answers in rectangular coordinates, though. So what are we looking at here? Answer 1. I've got cosine of 60 plus I sine 60. This is 1/2. This is root 3 over 2. So this gives me 2 times the 4th root of 2 plus 2 root 3 times the 4th root of 2i. And that's ugly looking. Am I right? A little bit ugly looking. That's how we're going to do the rest. Well, I'll leave that as an exercise for you guys to enjoy, because I know you're enjoying it already. Well, let's do all I need to show you. All right, we can also do, they give us this equation. They might give us the answer in equation form. Find all the complex roots of x to the 6th plus I equals 0. So I'll rewrite it. X to the 6th equals negative I, which is 0 minus I. Which is all the way around, right? Straight downward. This is cis 270. Radius is 1 because it's got a length of 1. There's no multiplier on it. So we're looking for how many roots? X to the 6th power. We want 6 roots. Well, r equals 1. And so the 6th root of r is the 6th root of 1, which is still 1. That's handy. Theta was 270 degrees. But this was x to the 6th power. This should be r to the 6th cis 6 theta. So 6 theta equals 270 plus 360 degrees K. $270 divided by 6, 45. Yep, 45. So 45 degrees plus 300 or plus 60 degrees. K. For K equals 0, 1, 2, 3, 4, and 5. So we have cis 45 cis 105, cis 165, cis 225, cis 285, and cis 345. You'll notice that when we graph it on a circle, .45 is right here. 105 is right there. 165 is right there. Exactly straight across is 225. Then we got 285, which is exactly straight across this one. And 345 is exactly straight across that one. It broke the circle up into 6 parts. The tips of the arrows are all exactly the same distance from each other. That's kind of neat. And that kind of wraps up what's going on in 8.6. 8.7, we're going to do some polar graphs. And 8.8, we're going to look at some parametric graphs. But we're done. We're really done with the big parts of it. You're not going to be graphing in polar very much, hardly ever. But I do need you to have seen it. Peace.